So hello and welcome everyone to Research Connection Speaker Series. This series highlights the relationships being built across our teams and the exciting work that is happening in the industries Autodesk serves. If you have an external speaker that you think is interesting, invite them to participate as a speaker in this program. I'll share a link in the chat. Right now, October and November are fairly open, so help me schedule those out. I'll now hand it over to Roger, Principal AI Research Scientist, to introduce today's speaker and give some insight into their connection. Roger.
Thank you, Haley. Yeah, it is my great pleasure to have Weilian here today to talk about Scan-to-BIM. So we've been working with Weilian and Yasu and his lab on this project for over a year. And recently, the paper about this project has been accepted to WACV 2023, which can take place in London in 2 months. So I think Scan-to-BIM is a very important topic, especially within Autodesk. I remember last year, Carl and I went to Korea and we visited some of our customers. And one of them mentioned that the reason that their employees stay up to 2 a.m. every day is because they have to manually convert point cloud and other format of data into BIM models by themselves. So, and they kept asking like when Revit can facilitate this kind of feature. So I think William's project is a very important step to this direction. So without further ado, Weilian, please take it over.
Yes, thank you, Roger, for the introduction. Let me share screen real quick, and then I can continue maybe. Great, hope you can see the screen. And awesome. And again, thank you, Roger, for introduction. Yes, this project has been going on for a good time now. This kind of large-scale project by nature, since we did have to collect some of our own data for the research. So, but yeah, thank you everyone for having me. And I also do see a very nice crowd. So thank you everyone for joining. Perhaps I think today's audience is like not just researchers or computer vision scientists. So I'll be happy to hear of all of your thoughts, any questions as well. For questions, I do have a few section breaks in the middle of my presentation. So I'll be collecting some during then and I can answer them. But just maybe a little bit about myself first. I am a 4th year PhD student at Simon Fraser University in Vancouver, Canada. Unfortunately, I don't think that's the view we get from our campus. I think that's actually from our rival school, UBC, but nonetheless. But before coming to SFU, I did my bachelor's and my master's at University of Kentucky. Kentucky is famous for horse racing, or Kentucky Fried Chicken. I guess that's probably more well-known. And during my time at UK, I studied under Dr. Nathan Jacobs on roadway safety estimation. So there was some close collaboration with the civil engineering department then. And now I'm studying under Professor Yasutaka Furukawa, which is also in our meeting today. And we have done a couple projects on floor plan reconstructions and automatic scan-to-BIM methods. And to highlight my supervisor's lab, here are a handful of topics that my friends, my colleagues have worked on, including structured reconstructions, IMU localization, CAD generation, and floor plan generation. There has been some amazing publications from these topics in the past few years in major conferences. And there are, of course, many other works. This is just a select few. So, and today, I have the pleasure of presenting our latest work in assistive scan-to-BIM modeling. And just one quick correction is actually to BMVC 2023 for the British Machine Vision Conference. So, so yeah, we're happy that it's accepted and we can publicly say that it's submitted somewhere. And as a disclaimer, I am not a civil engineer or architect by any stretch of imagination. So I do recognize that we have some BIM and maybe Revit experts in the audience today. So definitely do let me know of your thoughts or even perhaps criticisms. At the end of the day, we do want to create an application that people want to use. And this is perhaps a start towards assistive modeling tools, hopefully a good one. But we recognize that it's perhaps nowhere near refined enough for industry usage. So we definitely look forward to some next steps. But without further ado, let's first ask ourselves, what is building information modeling? I tried to explain this to a lab mate of mine the other day, actually, and I would say, at least as a computer vision person, that it is a 3D model of a building. But that would be kind of selling us short because it's much, much more than just 3D geometry. This 3D format is supposed to support the entire life cycle of a building. So that goes from design to construction to maintenance, and also very importantly, the eventual demolition of a building. And to support these functions, of course, it is at least a 3D model with a highly detailed geometry, and the geometries have well-defined semantics. And if you compare that to more general purpose CAD models, BIM is laser focused on building semantics here. So, and of course, Autodesk Revit support those with very high standards. And if we look at the Revit UI a little bit deeper, we see that we have a lot of element attributes and part relations that we can modify and apply. And in vision or graphics, most things are just like simple 3D volumes, but in reality, walls in this case are compound structures and have material properties. So this sort of highlights the complexity of BIM, even just on the geometry side of things. And finally, well, not finally, but beyond that too, BIM is something more than just architecture. It is a platform that supports collaboration with other disciplines like HVAC, mechanical, electrical, and plumbing. The advantage here is that during the design of the building, everyone here actually uses the same 3D model to perform the design. So it's almost like the Google Doc of building industry, I guess. And if you, so with that, collisions or anything can be detected and resolved before anything is built. And that saves a lot of time and money on that front. So again, like compared to your more general purpose CAD models, we of course at least have geometric data, but BIM supports much, much more, including like construction techniques, how walls are joined together. And for the civil industry, all these things corresponds to saving money and time, which is, I'm sure, very, very helpful. Now, you might be wondering, where do we actually get these BIM models? For new buildings, you would design them from scratch, but for existing buildings that have been built, but without using BIM, we rely on a technique called Scan-to-BIM, which is the process of obtaining these models for already built buildings. The process would start with a survey of the target building using a laser scanner, kind of like the one here, to obtain a point cloud. You would then hand the point cloud to an architect to perform building information modeling, and you will specify the level of details, like if you just want architectural stuff or even pipings, HVAC, and then you get the corresponding BIM model. Now, this scan-to-BIM process, as Roger mentioned, is a very labor-intensive task. You would need at least professional architects with this training, and also many hours of modeling time to perform one building. And this is a sentiment shared by architects as well. So according to the survey done on 169 architects, you will see that over 3/4 of them agree that this is indeed a very time-consuming process. And there does exist automatic solutions. These are some of the professional closed source ones that people have mentioned. But in that same survey, we also learned that about 1/3 of the architects do not use these tools actually. Then they explain that it might not have reasonable accuracies, the geometry might have errors, and it doesn't work for all situations. And that's also similar feedback we get from architects that we have worked with. It's just no one really wants to use these. It's just easier if you start from scratch instead. And there does exist open source, this one open source research code base from Bayesier et al. This is like a Dynamo package. But when I was first trying to use it, just looking at the installation guide for this, I felt rather intimidated. And if I feel like if I'm intimidated, then it's probably not very accessible to most architects to use. So that limits the adoption. So clearly, we do see that there is a need to speed up this modeling process. So our research goal is to create an assistive scan-to-BIM system, not necessarily fully automatic, but assistive, that can directly integrate with Revit, so that minimizes the friction jumping in and out of different software packages. We do want to achieve state-of-the-art reconstruction results for walls. And with the assistant it provides, it should offer natural modeling suggestions. And that's kind of a research interest, because to offer natural modeling suggestions, we decide that we want to learn from real modeling sequences from architects. So that's also like an avenue for new data, that there's not necessarily anything on the market for architect modeling sequence. And note that for now, for this project, we focus only on wall reconstruction, which you can say is a limitation of our method for now, but it does account for a large portion of the modeling steps of this process in general. So that's what we focus on for now. And I do want to show a quick demo of our system in action, just so you kind of get a sense of what we have created. Let me see if I can pull that up real quick. Oops. Oh, let me full screen. So this is all running inside Revit. I wish I could do a live demo, but unfortunately the workstation has some issues. So we had to settle with the video for now. So you would use a plugin first by, the user can initiate an action. So in this case, the user is first drawing the wall, and then our system would offer the suggestions here in pink, and then it can do so like forecast, like in this case, up to 3 steps events. So this solid pink line is the immediate next wall it wants to add, followed by this one, and then this one. And to accept the suggestions, the user can just simply click a button on the keyboard. So I'll let it play again. And the user can just kind of keep on clicking to get the next, accept the next suggestion. If the user doesn't like where the trajectory is going, then you can just click another button and then say, here, offer me some more next steps to choose from. And in this case, 3 candidates are created, and the user can also click another hotkey on the keyboard to choose red, green, or orange. And then clicking that, it will, and then things resume as normal. And the user just keeps on clicking. Now this is running in real time. And then if the user can also delete suggestions if it's actually not part of the model. So that's also another interactive part. And I'll touch on this a little bit more later, but our system accepts new corners. This is like a sort of not a native Revit geometry, but the user can add corners saying, okay, there are a couple new corners here. I would like to add a wall between these two. And with new corners, it also adds more wall suggestions. So this is, these are sort of like the few different modes that our software supports. And then maybe if I can show another quick one. This is like I'll let this kind of run on its own. This is trying to finish a half-finished model from scratch, not from scratch. And this kind of just shows you can just let the system basically just click the single button, and then you get half of the building finished fairly quickly. So that's the demo. Sorry, I'm gonna bring this back. Are there any questions by chance so far? I do see some things in the chat. Oh, no problem. Awesome. I guess no questions so far, so I'll go ahead and move on. So showing demo, I'll kind of start the official presentation now. I'll present some related work first, which is roughly split into the related data sets and methods, some relevant ones. So we are dealing with built environments, and there are plenty of indoor data sets available through the research over the years. Here we highlight three, which have been collected using either 3D scanners, that's Matterport 3D, RGBD cameras with ScanNet, or manual annotations in the wireframe dataset. These datasets mainly focus on residential buildings, which for our areas of interest, we want to focus more on commercial industrial buildings. So these datasets don't necessarily fit the bill. And also there are no ground truth BIM models for any of these buildings. And if we look at a larger scale, we have the data set of HoloCity. It's city scale with building CAD models. And it also has panoramas at many locations within the city. I believe this is London. And you can see on the top right, all the red dots are where we have panoramas for. And they're aligned in the CAD coordinate system. So you can just have kind of street view images at many locations in the city. The CAD models is interesting, although the data set only focus on the exterior of the building, so there are no details inside. That also fortunately doesn't work. And then we have also the Stanford 3D indoor data set, which consists of 6 large-scale indoor areas, including offices and lecture halls. And we would say that this data set is probably the most similar to ours, to our goal, except that for annotations, we want the more detailed BIM models instead of, in this case, I think it was just some segmentation results. And on the method side of things, to reconstruct building geometries, there has been a line of structure reconstruction algorithms from my supervisor's lab. Here are 3 to name. And over time, the algorithms require less and less heuristics and hard-code the geometry grammars. I think for raster geovector, it was more the junctions between walls were defined, and then using integer programming for optimizations. And eventually, with ComBMPN, we can have flexible topology and also a lot less assumptions. So there's no Manhattan's assumptions anymore, which is more closer to the real world case. And in CBPR 2022, we have the state of the art in reconstruction with heat. It can do structural reconstructions on satellite images plus point cloud density, point cloud density images. And just to give a quick high-level view of heat, the way it works is that it first detects corners within the image, and you can use corner detectors. In this case, I think they used a transformer network that treat each pixel as a node. And then you would then enumerate all possible corner pairs to get edges, and then you perform binary classification on each edge. And the main novelty for heat is the new image plus geometry fusion module inside of the edge classification part. And it's implemented as a special transformer attention layer. I do want to mention heat because our method actually uses it as the main reconstruction backbone. But we did have a few modifications to suit our data since it's a bit larger scale. And that's for related work. if there are no questions, I'll move on to.
We actually do have one question. So
yes.
Vladimir asked, other than walls, what other Revit 3D category objects can your software recognize in point cloud and insert in Revit as a Revit object? Does it work with structural framing, W columns, and W beams?
Yes. To put it plainly, right now only walls. It is rather simple. The data set. We had intentions of doors and windows, and even curtain grids as well, but unfortunately we weren't able to get to those because we're only looking at things from a top-down perspective first. It's kind of hard to detect doors and windows. Those are definitely available future works. I couldn't really catch the last part, the other wall or junction types. I think this is a part where I'm not necessarily a civil engineer, so this is all sort of new to me still. Yeah. I'm not sure if that answers the question. Okay, I'll take that as a yes for now. Oh, that's fair. Correct. The BIM model, the ones we've collected, which we'll show in a second, they do. So we do have, I think we model up to level of detail 200. So it is only a matter of time before we can get to modeling the other components. Okay, I'll maybe go ahead and move on for now. So for data, we have collected, for Scan-to-BIM in general, we do need point clouds of lots of buildings. So we borrowed many of them from the Below workshop, which is a CVPR workshop that has been hosted for 2-3 years now, CV for AEC. And we hired many architects through the freelancing platform called Upwork to obtain ground truth BIM models given point clouds. And one of our research focus is to learn from architect modeling sequences, which unfortunately Revit does not record this information. We haven't found any functionalities. So for this project, we had to create a custom Revit plugin that we asked architects to install, and it records their modeling sequences in the background and then exports them to a JSON file along with the BIM model. The plugin is, since it is a Revit plugin, it's written in C# and it fully utilizes the Revit API. As mentioned, it runs in the background during modeling, and it hooks itself up with a few Revit listeners, some event listeners, to record element states after each modify. And then if you take the element states and you kind of find a difference between them, you can figure out what the architect actually did. And then we wrote a custom replayer to read that data, and we can kind of replay the actions that the architects did. There were some other functionalities built in with like fail-safe checkpointing, because the modeling sessions can get quite long, multiple hours. So we don't want a bug in the middle to ruin the entire modeling session. So, and this is also like a snippet of what the data that we record. So this is just for a wall modification. So you see that we do have a lot of information here, and our research only utilizes a small portion of it. So there's a lot more that we're hoping people can look at and mine out of all of these JSON sequence data. Now, if you are familiar with Revit, you might know of a functionality called Revit journal files. This allows the recording and playback of a Revit session. And you might be asking, like, would journal files work instead? Why do you have to create a whole new plugin? We did try that, but unfortunately it didn't work for our case because the journal files, they're just very difficult to parse. It has like lots of other logging information, and it wasn't very reliable to play back for super long sessions. It's okay for like 15-20 minutes maybe, but any longer, we start to run into issues. And as far as I know, it doesn't necessarily record the Revit activity, but more so like the user interaction with this Revit session. So it's dependent on a lot of things like monitor resolutions, which we didn't like. And finally, there's no real easy checkpointing method. We haven't found a workaround. I think the architect has to restart Revit every time for a new journal file, which would have been a bit cumbersome. So, which hence warrants the creation of a new plugin. Just want to show some statistics for our data set. I think what is to know here is we have a total of 16 sites and averaging about 2,000 square meters each. And on average, also about 6 hours of modeling, I think up to 9 or 10, and then total of 90 hours of annotation time. And we have all of the architecture steps there. Here are some point cloud, BIM models that we collected with the corresponding point clouds. As you can see, these are like office type buildings, or I think also maybe just medical places, but fairly large scale data that we have collected. And to show the sort of the modeling history that we have collected, let me share another video. Hopefully, this is our replayer in action. This is of course sped up, but this is kind of replaying the data that we have collected, and we can see how the architects have been doing their modeling. And this is also them constructing the windows. Yes, so that's just a quick blurb. And as a side note, for input to our method, we process the point clouds to obtain a 2D point density slices. So we do for now, we're treating this almost like a top-down 2D problem, looking at the 2D point cloud density. We've horizontally sliced the point clouds at 6.56 and 8.2 meters. And within each slice, we project each point onto the floor and compute pixel density within 1 by 1 inch grids. And since we have 3 slices, we get 3 images, and this sort of treats it sort of like an RGB image as input to our method. We pick these thresholds sort of manually. It's pretty consistent across all of the buildings that we've tested with, and surprisingly, the above 8.2 is actually very useful in our case, because checking from the ceiling side, it's actually pretty easy to see where the walls are also, because normally when you can't see inside the wall, so those are just appear as black gaps. So yeah, that's the data pre-processing side. And not sure if there's any questions so far before we move on to the proposed system. Okay, I guess I'll go ahead and describe our system now. So we saw in the demo, this is just a quick recap, I guess. We have the current state of the BIM model. The user adds a wall, and our system suggests multiple walls kind of as a forecast as to where the architect might want to model next. If we look at that, if we break that process down a bit, we first have the current BIM model with the modeling history leading up to the last edge. We first pass the state into the candidate wall enumeration module to get walls that we haven't modeled yet. So that's all the blue walls that can potentially be added. We then pass both the existing and the candidate walls to the next wall prediction module to determine which wall is likely going to be added next. This just chooses one wall as the next one. But this last module, we can run it auto-regressively. So this way we can kind of obtain a forecast of arbitrary number of steps. And that is what we present at the front end through the UI. If we look at the first module in detail, Again, it's kind of inspired by the heat architecture. We begin with the 2D point density image, although there is an important note here because we're actually looking at the whole floor. The crop is just for visualization purpose. Otherwise, it's kind of hard to see the details. But for now, let's look at the whole floor. We predict corners, but since the image is much larger, we first predict locally in crops and then merge the predictions together, and we get the global corner map. If we zoom in now for the edges, we exhaustively enumerate all of the edge candidates and then use a transformer network to classify each one as being positive or a negative edge. And this is the place where we made an improvement over the heat architecture. We use a heat, you only uses one reference point to extract image features for the edge. In this case, we decided to use multiple reference points because an edge can be quite long and it might not make sense to just look at one area for the prediction. So we sample multiple points. And then finally, we consider all of the existing walls and then use an overlap heuristic to remove duplicates because we only want to suggest walls that haven't been modified yet. And that's what we provide for the next module for the next wall prediction. So with the output of the previous stage, we now choose which wall to add. And there's a subtlety here that we represent the order in reverse for consistency. But likely it doesn't really matter forward or reverse order. Our main backbone here is a transformer network. So we first construct input nodes to the network. And it consists of coordinate information, ordering, and also the type. Coordinates are represented by the walls to endpoint locations, so XY, XY. Order is just represented by an integer for the time step it was added in. Candidate walls will just all have 0 as the order. And also the type, just 0 for green and 1 for candidate walls. The order transformer network takes in these nodes and then outputs an embedding for each wall. And for the order transformer, it's essentially a 6-layer transformer, has 6 transformer blocks, and there's some encoding at the beginning to convert the information into higher dimensions, and also some linear layers. The encoding for the coordinates and the order, we use cosine embeddings. And then for the type, we use a learnable embedding instead. Those are just subtle details. And then once we have the embedding for each wall, we can compute the cosine similarity score between the last added wall and a candidate wall to obtain sort of a probability score, but it's just kind of a likelihood. So this is the last added, so like this is the last added wall here with the order of 1. And then this is one of the candidate walls, and this is the this is a score for how likely it should be added next. And we can compute the score with respect to all candidate edges. And then we would just pick the one with the highest similarity as the next wall to add. To train this network, the objective will be to maximize the score of the ground truth next wall and minimize the scores of all of the other candidate walls. So to do that, we just use the triplet loss. And the anchor will be the green wall, and positive will be the ground truth next wall, and negative will be every other ones. And we train only on ground truth edges and sequences. And we found that during evaluation, when we have to use predicted edges, it also still worked pretty well. So there's not a huge train test discrepancy in our case. Yes, so that's how we also train the network. And there is also one more detail that for wall orders, we only go up to 10. I think through the experiments, we tried remembering more walls, but it seems like anything past 10 steps ago doesn't really seem to help with the immediate next step. So we just capped it at 10 for our case. And with the networks trained, we have a couple modes of operation. We can either let it run automatically without any user interaction, so it just kind of goes on its own, or in the assistive mode, like we saw in the beginning with the user able to choose different paths or delete suggestions. And that's a high level view of the method itself. Are there any questions so far again?
Looks like we have another one.
Yes.
Does your system have any tolerance setting to achieve best fit approach versus precise following of the point cloud? For example, regular walls may have various angles that differs from 90 degrees. For 3D Revit modeling, we often use best fit, so we would reasonably deviate from point cloud to create somewhat idealized model. It can be more practical versus premise model based on a point cloud.
Interesting question. Yes. There is no module right now that allows deviation. It will faithfully try to follow the point cloud as much as it can for now. So I understand that some architects, they don't like off-axis walls, and for our case, we don't necessarily restrict those. We just kind of let it follow whatever the point cloud is. I think all of those restrictions or constraints, if we can kind of describe it, it's probably possible to implement it in our system. Those are just more post-processing, perhaps, that we can apply to our predictions. Hopefully that answers the questions.
This is Yasu. Maybe this is a very interesting question. So my answer as being a bit irresponsible AI researcher, data. You have lots of data. With a bit of a deviation, the neural network or machine learning can learn to deviate. So as long as you have data, yes, we can probably do something. But right now there is no data. It's easier to say enforce 90 degrees. So that would be my answer.
Yes, thank you. Okay, I guess I'll continue for now. So for results, we will mainly be looking at, there are kind of two parts to it, because we do have a reconstruction module, so we will see some quantitative results there, and then we will look at some examples of the ordering. So first, we can look at a study on the effect of the number of reference points. And if you remember, that's kind of the modification we made to heat to consider image features along the entire edge instead of just at one point. And we consider 1, 8, and 16 reference points along an edge, which if you consider it, if we only use 1 point, that's basically the vanilla heat architecture. So that's kind of the first row. That's sort of our baseline for reconstruction. And the metric we're computing here is the precision recall of edges at different thresholds. What do we mean by that? So if we have a predictive wall, we consider it to be correct if each endpoint of the wall is within a certain threshold to a ground truth wall. So it could be 5 inches, or we loosen it up to 30 inches in this case. And the kind of the trend for the results that we can see is that more reference points, the better. Compared to the vanilla heat module, we have like a couple percentage points above it, from the baseline. But we do see that it is kind of with diminishing returns, because there's not a huge difference between maybe 8 or 16 reference points. So that's but at least the improved attention does help with the results. And for order evaluation, there's also actually a big question here when we first got here, because we're not really sure how do you evaluate an order, because it can be ambiguous sometimes. like adding this edge or this edge in this case, like the two options, both of them actually kind of make sense. And during evaluation, we do have, in some sense, like a ground truth from one architect, what he or she decided to do, but we don't necessarily want to enforce that. That's kind of a very harsh penalty. So, so we actually introduced a novel ordering metric based on the FID score. So FID score is a popular metric for evaluating image generation models. And to do that, they compute the, I actually don't know how to appreciate distance between between like a group of generated and a group of real images. So finding the similarity at the kind of the high level end, not necessarily between individual pictures. So for our case, we replace images with sequences, and normally for FID scores, you use a pre-trained convolutional neural network to perform image feature extractions. In our case, we instead use a temporal convolutional network pre-trained on an autoencoding task, and we get like one embedding vector for each predicted sequence, and then we compute the free shade distance between them. Note that for in this case, since we use a TCN, we do look at sequences of similar lengths, so not necessarily between different lengths. And with the new metric, we also have a couple of baseline methods that we considered for order prediction. The first one is a simple heuristic that always picks the closest edge to the last one. So this kind of just ignores any history information. And in this case, the green edge is closest to this pink edge, so it will pick this one as the next one. And the second baseline is a more straightforward approach compared to ours, by just training a classifier to look at a full sequence and predict a binary probability whether if this is a valid sequence or not. And for the classifier, since it only looks at one sequence at a time, we just need to enumerate all possible sequences, classify each one, and then choose the highest. And with the metric and the baseline, we can now look at the result. One thing to note for this plot is that we're first simplifying the problem a bit by using only ground truth walls. So candidate walls, the blue walls that we saw before, in this case, they're ground truth instead of predictions from our network. So in that setting, we can see that our method in green is consistently lower than all of the other methods at all sequence lengths. FID score, the lower is better because lower is more similar to ground truth examples. And it is a similar trend when we use predicted walls instead, although the gap between classifier and our method is closer, the blue and green curve. We believe this is due to the reconstruction results. As our reconstruction results get closer to ground truth, things will look more like the left plot instead. And to look at things more qualitatively, we can also visualize some of the predicted orders that we have. So for the first three columns, these are our baseline methods. And the fourth column is the ground truth order. And the green walls between the columns stays the same because these are the conditions that we provide to the model. So these are kind of, we're simulating, these are the past 5 steps that the architects have performed. And we ask the method to predict the next 5. And as we can see, our method generates orders closer to the ground truth on the right, in this case. And also for another example, we can see it decides to follow the last wall to model the bottom right. So that's, yes, those are 2 examples for our ordering method. And that's for the results. Maybe I'll go through conclusions real quick because I think there is some important things to discuss about the limitations of our method. So as far as limitations, there's kind of three parts. There's like the data set, and for our method, there's two parts with the reconstruction and the ordering. I mentioned that we do have data for constructions for modeling sequence, and that's great. Although for replay, there will be some reliability that needs to be considered. So that's kind of the data itself. Sometimes replay, Revit is like a very complex system. Every time you move one thing, like half of the other thing in the model also updates itself. We do capture all of those changes, but that's sometimes kind of hard to replicate when we're doing a replay. So that's something that can have some more engineering put into it. And with the evaluation table, you also saw that our thresholds are like 5 to 30 inches, which compared to the precisions you normally need for the industry, that's probably like the Grand Canyon. So we do want to improve reconstruction results. And that's a little difficult right now with the small data set that we have with only 16 sites. So we do hope to collect some more data to fix that front. Because you can see, hopefully, with these results, we have missed this wall here, so we aren't able to really offer good suggestions to the architect, which the architect can always intervene in this case, but there's still much to improve from the reconstruction side of things. Yes, so you can see our method also struggles with areas that these boundaries where perhaps no one went into this area to scan, or for some reason this area doesn't have any point cloud scans, and things can just kind of miss in an area. And lastly, for ordering, order can still be sometimes a bit unnatural. We witnessed some examples of this. Kind of depends on how many, like if the architect all of a sudden goes to a different area to model, sometimes our method is hard to let go of the previous area and still recommend in the previous area instead of the new place. Because like here, it should start modeling here. This is the ground truth, but then the method still is stuck with the previous old place. So that can cause some frictions and maybe make the architect not waste some time in there. And so that's just some limitations. And I do want to acknowledge all of the support that we received for this project, including grants. Shout out to the workshop for providing the point clouds, and also to all of my collaborators for helping with this project. It has been going on for some time, and just do want to thank everyone for the patience and all the suggestions that they have provided. Thank you, and I will continue to take the questions now. There is a project webpage up, and also my contact information is there. The code and the data for the plugin, for the recording, for the replay, everything will be available. We are still currently preparing it, so do stay tuned and check the page often for updates. Yes, so thank you very much for your time.
Thank you so much. If you have questions, please feel free to drop them in the chat, put them in Q&A, raise your hand, come off mute, ask it live.
Hey, Weilian, thank you so much for this great presentation. I do have a question regarding the data.
Yes.
Like data shortage is the major limitation to move it forward. Say if we have like a magic source that can get us data, how many data do you think we need to take this project into the next level?
That's a good question. My impression is at least the number of sites should be like in the thousands. So that's probably at least like 100 times. That's kind of ideal. I don't know if my advisor has different opinions. So if we only have 16 for now, maybe like 1600 is kind of a number to shoot for. But yeah, that's
similar.
Just my guess.
100 times more, maybe 1,000. Those ranges. 2 more digits or 3 more. Yes.
Thanks.
Yes.
Great.
Yes. I see someone raised their hand.
Yeah. So I was wondering, you mentioned that you had two modes of operation, automatic and sort of user, like with the user interaction.
Yes.
I don't think you showed a comparison and performance between them because I think your results focused on the order of the wall placements as opposed to the overall results. I'm just wondering if you had any way to compare like the end result, the quality of the end result between these two cases.
I see. I guess the two modes maybe just to know, like the two modes are simply different ways to present the order, like the reconstruction results. Like if the architect cares about the quality of the reconstruction, at the end of the day, these two modes actually are the same because it uses the same module to get the wall candidates. So I'm not sure if it's if there's a way to directly compare the two. These are just two modes that the architects might want to use the software. But through the assist. Oh, go ahead. Sorry.
Yeah, sorry. Just to clarify, sort of the end result. Like, say they played through to the very end. The end result is exactly the same. So all the possible I guess the possible walls don't depend on the order. For the assisted case, the walls don't depend on the order in which they go through. It's always the same results in the end. Is that true or?
Yes, the change in ordering doesn't necessarily affect the reconstruction results. Although for the assistant mode, we expect the architect to change something in the middle. As soon as the architect make changes to an existing wall or existing corner, then things get rerun in the back end for better suggestions, for better reconstructions.
Oh, okay.
Actually, maybe, not sure.
Okay.
Perhaps there's some confusion.
but it's okay. So so with the interaction, it has the potential to change the result if the user decides to intervene. So I guess you could do a study where you put this in front of several users and see if they intervene and make manual edits and see if that results in a higher quality design at the end.
Oh yes, that is something we actually were hoping to do, like a user study, except unfortunately we didn't have enough time. But yes, it's there were like maybe a couple things we wanted to measure with like improving reconstruction and also just in general like the speed up. We're expecting those two things to at least be boosted from our system.
Yeah, great, thanks.
Yes, thank you. Not sure if there are any other questions by chance.
Feel free to raise your hand or come off mute if you have another question.
Maybe I can also mention. Oh, sorry. Did someone say something?
I was going to ask another one then.
Yes.
But yeah, just curious. You thought about like if you've looked into these other types of data, I think you did mention them in some of the related work. But I'm sort of curious, like, what are your thoughts on this? Is using point cloud, but you could also like a cheaper way to get data would be just to walk around a building with a smartphone and taking pictures or something like that. Like how are you interested in these different types of data, or do you have an opinion on which ones are more promising?
Yes. I think at least for the point clouds we collect, it's all a matter of precision at the end of the day, I suppose. Because for the point clouds, they were using some pretty fancy scanners, like sub-centimeter accuracy points. So that would of course gives us the best reconstruction quality. But if we do want to extend past walls to like doors and perhaps even more complicated structures like stairs, I was trying to look at the point cloud to see how we would be able to tackle those things, but sometimes the points, they just sometimes gets a little sparse and it's hard to tell exactly where the boundaries of things are. And that's where matching RGBD videos will likely play a bigger role because it's it's easy to just it's easy to collect videos or images at multiple viewpoints, much more viewpoints than you can with like placing a laser scanner down somewhere, scan, move it, they'll scan. That's kind of cumbersome. If you just have a kind of like a scan data of some points and then supplement it with dense video footage, then you probably have everything you need to do the reconstruction. So
Yeah, great. That's insightful. Thanks.
yes. And during research, there's something else that kind of comes up with, at least on the order side, is like every architect kind of models differently. So it will be interesting maybe as a future consideration to see how we collect the same building but from different architects, and they will likely have different order preferences, and we can kind of either generalize to all of them or figure out a way to offer more personally tailored suggestions based on your own past modeling history. So that's also interesting.
Yeah, I agreed with you actually when you said that, like, I mean, it seems like the metric that you're currently using might be a bit too demanding because it penalizes your results if like your algorithm decides to start one area rather than another. But it probably doesn't matter that much as long as when you choose an area, the sequence flows. So yeah, I think having that a greater diversity of ground truth to work with, and maybe a little bit more flexibility, like for example, showing multiple different areas to start might show that your method does better than
yes
than you showed, than these current results show.
yes indeed. I think having more variety is yeah, it's more on like, I guess we're kind of letting the data itself handle the problem. Like if we have more variety in the data, then theoretically our evaluation is more flexible. So yes.
Great.
Yeah.
Well, thank you so much. We're at time, so this was wonderful, and we look forward to seeing more work from you in the future.
Yes. Yes, thank you very much, everyone, for having me, and for Roger for letting me present the work. Yes, and do feel free to contact me or just visit the webpage for updates. And yeah.
Wonderful. Thank you.
Yes,
Thank you.
thank you very much.